Great. Thank you for the introduction. So today I'll be telling you a little bit about some of our recent work done in collaboration with Chris Pattison, who was an intern with me, as well as Gefen, Pablo, and Misha from Harvard. And we'll be talking about how to improve the methods of performing quantum interconnects as we think about large-scale fault-tolerant quantum computer systems. So as we think about where we are today with our quantum computers and where we want to be, we're currently in something like a couple hundred qubits, physical error rates of around 10 to the minus 2 or so. Very impressive systems to some degree, but at the same time also very different from where we might eventually want to be with maybe tens of millions of physical qubits eventually reaching 10 to the minus 15 error rates. And really the goal here is to both make the system much larger, but also make the system much better as we're running large-scale algorithms. And so as we think about the construction of such a large-scale system, it's very natural to ask what are maybe some ways, or at least basic motifs, that can help us simplify that construction. For example, if we have an individual node, perhaps constructing many independent quantum computers and then linking them together could be a good strategy, because you get scalability, you're printing out many copies, which might make it easier to benefit from economies of scale. You might have modularity. You can kind of decouple the intranode and internode engineering challenges. If one of them breaks, you can just take that offline and perhaps do maintenance. And also, along the same lines, there's more robustness in which you're more tolerant to failures of a given node. And so this sounds like a very good approach, but why isn't this already being very widely pursued? Why is it something that people haven't really investigated as much? And really, a large part of the challenge is that making these interconnects is very hard from multiple aspects. On the one hand, interconnecting these nodes often involves optical or microwave photons, which therefore involves a conversion from the native degrees of freedom that your superconducting qubit or trapped ion or neutral atom system might be natively encoding the information into some itinerant degree of freedom that allows you to send this information and communicate it. And so this conversion usually is pretty slow and noisy. For example, if we look at some state-of-the-art numbers in atomic or in this case, ion trap systems, you're looking at something like around 95% or so fidelity with a 200 hertz rate. And now if we think about these large-scale error-corrected systems, we're typically hoping for a rate that might be something more like kind of a megahertz or at least kilohertz clock speed. So already at the physical level, your clock speed is slower than what you want at the logical level. At the same time, these fidelities are also quite some distance from what you would want for the thresholds. As we heard in the previous talk, typically we're looking at a 1% or so error threshold in the bulk of an error-corrected computation. And so both the fidelities and the rates are quite far away from what we would want to have, and therefore we want to have techniques that allow us to bridge this gap. So the basic idea of being able to bridge this gap is very well known in the community. This is the idea of entanglement distillation, first pioneered by Bennett and others in the 1980s. The idea is that you have some physical bell pairs that you initially have, they're pretty noisy, and we want to be able to distill a smaller number but much higher fidelity copies using this entanglement distillation procedure. So there will naturally be some overhead of running this procedure, going from a certain number of physical qubits to a certain number of logical bell pairs. And this overhead is what one would like to optimize so that we can most effectively make use of the resources. So in our contribution, we studied this problem and tried to analyze it and improve the protocols. And in particular, what we developed are entanglement distillation methods that allow us to achieve asymptotically constant quantum communication overhead. So you can think of this as somewhat analogous to the interest in the computational quantum codes perspective, in which people have developed high-rate codes that allow one to perform much more efficient physical to logical qubit encodings. In this case, we're trying to generalize these ideas to the setting of communication between multiple nodes, which we'll see introduces different considerations and how we can optimize things. To do so, we carefully select a code concatenation sequence of how we're doing this distillation using quantum error detection such that we can both have theoretical guarantees on the distillation and overhead and performance, and then further perform numerical optimization across code families to quickly identify promising families that might reduce the overhead. And the upshot is that compared to the standard schemes that people had, either using lattice surgery to directly connect the nodes, or using techniques such as 2-to-1 distillation with repeated repetition, that's the standard Bennett et al. Distillation scheme, we can achieve a 10x overhead reduction in the amount of communication overhead required. So just going into more detail of the setup here, we'll think of here just simplistically just as having 2 nodes with some networking area in addition to the compute. We'll allow 2-way classical communication between these 2 nodes, which allow us to coordinate the actions, and in particular say that if we run some protocol and we detect some errors, we can just discard that copy on both sides and start over again with a cleaner copy once it passed this error detection like check. This allows us to start with bell pairs with lower fidelity because we can more effectively filter out errors and achieve high encoding rates. The next step, the next kind of basic procedure that we use is that after we distribute the physical bell pairs, we actually inject these physical bell pairs into individual code blocks such that we can utilize the intranode protection provided by the high fidelity kind of within node operations. And so we want to really, because this communication link is so noisy, we want to reduce the amount that we're communicating across the node and kind of using the fact that we can have high fidelity locally corrected operations. And so this allows us to bound the effect of local operations effectively to make them negligible and use the communication channel more efficiently. What we then do is use a concatenated procedure in which you first do some error detecting distillation of entanglement distillation on the left, and then you take these outputs and then you further encode them into multiple copies to do a 2nd level and 3rd level distillation. These distillations, they'll pass whenever no errors are detected in this code, so we're using codes in an error detection mode. Because the outputs of these might be correlated, we have to put them into independent copies, which we account for in terms of the resources. So then the key idea here, which actually builds on top of some work from previously in the computation setting from University of Tokyo, is to concatenate a series of error-correcting codes, in this case error-detecting codes. And if we use higher and higher rates, then the amount of overhead that we're paying at each later level will become less and less. And so the total combined overhead can then become constant. I'll go into a little bit more detail in a moment. I'll just quickly flash kind of the technical theorem that we were able to show. And in particular, for the theoretical analysis, we'll just be using this very simple code sequence where you have 4n squared qubits and 4n squared minus 2 encoded qubits. So as we go to higher and higher levels, we're using more and more efficient encodings, and we'll see why this gives us low enough errors as we go and kind of distill to higher and higher fidelities. So the intuition here is really when we think about the failure of this procedure in producing high fidelity logical bell pairs, there's 2 types of failures. Either the distillation can fail, which contributes some cost, or there's just some rate at which we're taking physical to logical qubits at each level. So the error suppression is exponential in the number of levels. And what this means is that when we go to higher and higher levels of this distillation procedure, the effective error rate at this level is now much lower, right? Because we've already distilled several rounds. And so the failure rate at higher levels becomes negligible, but also using a high rate code is then more okay because we're in some sense already such low error that the chance of failing is just already anyway quite low. And so using this code sequence, we can kind of take the multiplication of just all of the rates in all of the procedures as well as the failure rates and find that indeed the combined overhead is a constant. But in practice, of course, we want to optimize such a code sequence utilizing these ideas. And so essentially what we'll now do is to perform a numerical optimization over the different possible code sequences to find really the ones that might work well in different practical regimes and navigate the space of different trade-offs. So we optimized over a wide variety of different quantum and classical codes. One of them is this very high rate error detecting code that you saw earlier. But we also can just look up code tables. There's this very nice website by Grasswood on the internet that you can just look at all of the error correcting codes of a certain n, k, and d parameter, the number of qubits and the code distance. And then we just basically do a numerical search over these with some pruning to make sure that we can kind of do depth first search, bound the error rates at each level, and target the logical error rates that we would want in a large scale system, kind of these 10 to the minus 12 or so logical error rates. So with this, our optimization finds various code sequences for each of the different operating points. So on the different curves that you see here are the different distillation input error rates. And what we see is that as you make the distillation input better and better, of course, you'll have a lower overhead. When we allow this distillation to use more and more buffer memory size, basically allowing yourself to use larger and more efficient codes, we also see that the overhead of how many physical qubits are needed per logical bell pair reduces. So that makes sense and gives us a continuous trade-off between these different types of resources. What we also see here is that even with just a buffer size of around 10 or so logical qubits, you can already have an overhead that is quite low. So with several tens, we're looking at a physical qubit, like 3 physical bell pairs per logical bell pair, if your input bell pair error rate is relatively low. We can compare this with the existing methods that people have that I alluded to earlier. So one of the standard techniques that people had on the very left there is the original protocol from Bennett et al., in which you basically just do a kind of a 2-1-2 classical repetition code in alternating bases to purify these qubits. So this allows you to improve the fidelity, but you're using a code with a pretty poor rate. And so in some sense, at later stages of distillation, you're not doing things as efficiently, and this is reflected in the fact that you do indeed end up needing to pay a slightly larger overhead. The second and third row here correspond to that protocol. An alternative approach that people have explored is basically to just directly do lattice surgery, which is a commonly used error-corrected gate between logical qubits. In this case, you need to distribute bell pairs across the seam. Because these bell pairs are noisy, that starts to compromise a little bit how much resources you're using. And so effectively here in this scheme, you're really treating the local fidelity resources and the network resources as almost equal, which is why here you also end up paying quite a bit of overhead when running this lattice surgery scheme, because you're essentially you're paying the resources of the fidelity directly across the seam. So in our scheme, we're able to achieve much lower overheads. For example, if we have a buffer size of 100, you'll see that this overhead is about an order of magnitude less than these other existing schemes. And also, in this case, there's a variety of different trade-offs that one can try to navigate, depending on whether the fidelity or rate of the networking is the bottleneck, or whether the local memory buffer might eventually also become a bottleneck. And so I think it will be interesting to investigate in individual physical systems which of these approaches really makes the most sense. In our paper, we also analyzed, just in the setting of an actual distributed computation, how we should think about these various trade-offs. I won't go into the detail here, but basically, at least for current numbers, what you conclude is that the communication does often still end up being the bottleneck, and so these techniques that we're developing for reducing this communication overhead do seem to be very important in practice. And you can read the paper for the full details of this. So in conclusion, by using a sequence of increasing rate codes, we're able to achieve constant rate entanglement distillation and use these communication interface, which is quite costly, much more effectively. This gives us an order of magnitude reduction in the communication overhead, which we hope can help address the bottleneck of distributing computations between different nodes. So I think looking ahead, we also want to further analyze a lot of the details of the pipelining here. We did some analysis in the current paper, but these can be further extended for given systems. And also really understanding, as we think about large-scale compilation, there's a lot of interesting questions as to where exactly the entanglement needs to be distributed, how do we effectively architect the algorithms around those considerations. I think these are all interesting things that can also be co-designed with some of the error correction and entanglement distillation considerations I mentioned here. So with that, I'd like to acknowledge my collaborators and thank you for your attention.